Sagiv.
Thank you very much. I'm excited to be here. I'm going to talk about a new baby company which was established just in November, but it's actually leverages a lot of research that me and my colleagues have been done in the last 30 years, and I also acknowledge generous funding that we received from the European Foundation. Also I would like to acknowledge the team. I have not done anything here. That's the R&D team in Israel, in the company, Shelly Grossman, Marcelo Taube, and Sagiv Katz. They developed these tools, which I will be able to demonstrate for you, and actually you can use it. It's a tool for formal verification. So what is formal verification? Formal verification is a technology which accepts two inputs. It accepts the, this doesn't work, but it accepts the contract on one hand, and it accepts the requirement on the other hand. And formal verification can do two things for you. One thing that you've seen in the last talk, which is very interesting, that formal verification can produce a proof that it's correct. But the other thing, which is equally interesting, and in some cases more interesting, it can reveal bugs. It can reveal subtle bugs of your system. And you will see that our tool actually produced for you a concrete execution, not just symbolic, that demonstrate the bugs that happen. So smart contract, it's a domain that really needs formal verification. And I'm sure I don't need to convince you that in this audience, but it's important to understand that because we think that code is the law, so if we have a buggy code, we have a buggy law. And in some sense, it makes the situation worse than it happened before the blockchain. And another problem that happens, since we are in a decentralized world, actually once you identify a bug, it's a race to mitigate and actually find out, it's not like in a centralized session. So what happens if you find a bug, it's really hard to mitigate this bug. And what we do with formal verification, we really look for bugs. And we can identify subtle bugs, like we enter this bug, hijacking bugs. We can identify these bugs with formal verification. And also, as you have seen in Martin's talk, we can show their absence. We can do both of these things. And that's very interesting in this domain. So since I come from this domain, I would like to point out to you something that some of you are aware of, but not all of you are aware of, that formal verification in the last 20 years actually have made a lot of progress despite the difficult problems. And one area where it was very fruitful is the domain of verification of device driver. How many of you knows about the verification of the device driver? Maybe you raise your hands. It sounds like few of you know. So what is the case of device driver? The issue is that Microsoft Corporation, they actually allow third party to actually produce their own device driver. So they write device driver, and these device driver, they interact with the operating system. So this means that if you have a bug in your device driver, it can actually crash the operating system. So you've probably seen it if you are old enough. You have seen these kind of things. You have seen this blue screen. Maybe they are not as bad as stealing your money, but they're still devastating. And in fact, the last few years, we are seeing fewer of those. And part of the reason, believe it or not, is formal verification. And what happened? The Microsoft research team has actually taken a huge effort, which actually also followed by University of Berkeley and others, and incorporated many techniques, including my own algorithm for my postdoc. But the idea there is that you take rules. These are correctness rules. These are rules that says that every time you take a driver, you actually, every time you acquire a lock, you release it. So these are some of correctness rules for the driver. And basically what happened is that the Microsoft team, they developed this very, very nice algorithm, and this algorithm is fully automatic. The user is not aware of anything. The user only has to write the slick rules. It's a fully automatic method. And this method, it's true, the problem is very hard. We heard about the Rice theorem and others, but in fact, these algorithms solve it on C programs. You write your C program, you download it, you check this thing, and basically the tool either gives you an error or it actually shows you that the program obeys these rules. And this is a very nice quote from Bill Gates about this technology. I hope you can read it from the back, hopefully. But basically what it says is that this area of formal verification, which has been the holy grail of computer science, in fact, the Microsoft Corporation developed this technology which can be useful of program of medium size. And that's a very nice technique. And what we are trying to do in this company is doing something which is inspired by that for the blockchain. We are trying to build this automatic technology that can reason about your code, either prove properties or find you automatically bugs. And one of the things which is not very clear for people in program verification, I should say, my background is academic, but I spent like 3 or 4 years in IBM, and that shaped my whole thinking. And one of the things they told us in IBM that there are no such things as obstacles. There are only challenges. So in program verification, there are actually 2 challenges. One challenge is the technological, but the other challenge, which is equally interesting, is the challenge of the specification. How do you specify the right behavior? Okay? And what do you mean? How do you specify the right behavior for contract? How do we know which contract is correct and which contract is not correct? And this is somehow analogous to the Microsoft device driver rules. And in the Microsoft driver rules, I do not know if you are familiar with, these are all informal rules. But in fact, we need to have some kind of rules that say what is a correct smart contract. So in this talk, I'm going to focus on the first one. I'm only going to talk about the specification. I will talk a little bit, I will tell you about our technology, and of course, the articles based on our technology are all public domain. But I will focus mainly on the problem of specifying the correctness. How do you even say that the contract is correct? Okay. So I will talk about 2 kinds of properties that are interesting for smart contracts. And both are interesting. The first one are generic properties. So what do we mean by generic properties? This is something which is known in this community, and it comes in different domains. The idea is that we want to have some correctness property that will be fulfilled by all contracts. So it means if your contract do not fulfill it, you actually don't want to deploy this contract. And the question is, what are these properties for smart contract? The second thing that I will talk about are properties which are specific to a use case. For example, suppose you are building a stable coin or you are building an ERC20, what are the properties that you want to satisfy there? So let's go into the reentrancy attack. We have heard about it many, many times. You have someone depositing your money, you deposit some coins, and then later on somebody else deposits the coin, and then all of a sudden the thief comes, he or she deposits a little money, and then it all depletes all your money. That's not a good thing, and we would like to prevent it. This is a kind of problem that we would like to prevent. And in fact, interestingly, we can prevent this, and we can prevent it in all contracts. So what is the idea? The idea is, in fact, that we want to avoid this kind of situation. And the interesting thing is that some of these situations, for example, today, they are avoided in the EVM by the guards. But that's not a good idea. We have seen it in the Constantinople, because it means that when you upgrade your EVM, you're going to have these bugs coming. So you want to prevent these kind of bugs. And what we do in the company, we have a method which we actually enforce, that we check that each contract obeys this property. And if this contract violates this property, we reproduce the bug for you. And if your contract obeys this property, we can actually prove to you that this kind of bug cannot happen. And it also has another interesting thing that says that your code is somewhat isolated from the code that you are invoking. So it gives you this nice software property. And the property that we enforce, maybe I cannot sort of explain it in details here, but the idea is that, in fact, we enforce something which is very similar to what happened in the database. It's the idea of atomicity. So what happened? You see that I have the blue contract, and the blue contract executes occasionally, and then there's a purple contract, and then there's the green contract. So basically, in the Ethereum, they can all run separately. But in fact, the system is showing that there exists an equivalent execution in which they all occur continuously. So this is something that our tool enforces. It enforces the fact that all of the contracts, they appear as atomic. Even if they are not atomic, you, as a programmer, you can think about them as atomic. So this gives you some kind of criteria for correctness. And we can prove that statically, before the code is executed. Or we can identify the bugs for you. So that's the first thing that we do. That's good. That's generic. But as we know, generic properties are not the end. We need to, in order to get the good benefit of the verification, we need to reason about many things. And that's what we are doing with this. We have a method to define, we have a language for defining the properties of the contract. And we call it the contract vulnerability language. It's a language that we are currently designing. It is publicly available. And it actually allows us to express the property that we care about, like ERC20, like properties of a money market, or other properties. And this is a language that defines the property that we care about. And we are hoping to define this language as a joint effort with the community. And the interesting thing about this language is that it's reusable in the sense that one contract, one CVL actually covers many contracts. So when you write this one CVL, for example, we have this one CVL that covers all the properties in the ERC20. And now we are developing another one for 721 and so on. So basically we have a language and we have the ability to write reusable specification. Another property of it is it's verifiable. And we think about it as some kind of a system test, in a sense that you check the interactions between your contract. I'll give you some examples. It will be a bit technical, but hopefully you will get at least the feeling of what we are doing. So before I go to this, I'm not able to point. So before I go to that, I want to somehow explain to you how the technology works. So you see, we have, on the right, we have the technology AEV. We have our technology. We run the compiler. We compile the smart contract into the EVM. And then what we do, the programmer or somebody else, it can be us, you write the CVL on the other side, and then basically the technology either give you a verification report telling you the vulnerability does not exist, or it gives you the exact vulnerability and it gives you an input that shows you the vulnerability. And you notice again that somehow this is how these technologies work. It compares the smart contract according to the way you write it to the specification, to the requirement of what it means for this contract to be correct. So in the design of this language, and we should say it's a language is being currently developed, at the moment we have 3 principles, and probably we're going to add more. The first principle is generalization, the other one is mass is a law, which actually goes back to James Bjorner, and the third one is relating state, which actually takes care of the problem that Martin was telling you about. So let's see the generalization principle. The generalization is a very, very nice idea that came from verification. So here is a quiz for you. You have 2 programs in Solidity. Are these programs equivalent? You probably don't care. But these are programs that people write, and they write this kind of code. For example, they try to optimize gas, and they're trying to check that these 2 pieces of code are equivalent. So these are pieces in Solidity. In order to see if they are equivalent, what happened, you see, we show the CVL. Okay, we are showing the CVL here. Okay, so the first thing that you see, the first command that you see in the CVL, we havoc the first 2 arguments. What does it mean that we havoc the first 2 arguments? This looks probably weird to you. It's some kind of assumption that we say, we don't know what's these values. We want to actually verify this under arbitrary scenario. Okay, it's like kind of we havoc the value. And then you see that we actually execute the first, we call the first function, we call foo, and then we call the second function we call bar. So we are basically, it's just like a test harness. We run this code. And at the end, you see that we execute a command which is called static assert. Static assert is like the solidity assert, but it's executed statically. Okay, so it means that it's going to be checked on all execution passes. And basically, it will be checked against an arbitrary value. And we can run this tool, and we ask if this is correct or not. Again, I was not brave enough to run it. So you see, this is the output of the tool. A bit hard to read now. But what happened is that the tool actually identified cases. It's identified a corner case. It basically told you that for one corner case, foo and bar are not equivalent. So it's automatically identified the error for you, and of course, we're going to make sure that you're not going to exploit it. But we can give you a contract, and we can automatically identify the error for you. Okay, for example, here is a fix, also taken from the internet. So you see people are using something like the safe bus, and you see that they are using complex logic. Again, you see the CVL, it's exactly the same kind of CVL. And I'm running the same CVL again, and here it will tell you that it automatically proved, without the help of the user, that this kind of vulnerability cannot happen. So it's actually proved that for no input, this can happen, okay? And what it essentially proves is for all the arguments, arg1, arg2, arg3, it must be the case that foo arg1, arg2, arg3 is equivalent to bar arg1, arg2, arg3. And you can identify and you can give it all kind of complicated code, and it will tell you this answer. So that's the first principle. The second principle is actually more interesting. We want to shift from the case that code is the law, because for us and for our customer, mass is the law, not the code is the law. So basically, we want the programmer to write the spec in mass. And that's, of course, something that we borrow from VDM and other cases. So you see this example. This is, again, code. And this code is actually, you see, it's a function that iterates over a list, and it basically sums the element. So what we see is that we havoc the coins. We generalize the coin. We don't care about the particular coins. And then you see that we check that the result which is produced by the code, is equivalent to the mathematical definition. Notice that on the right-hand side, we can write arbitrary mathematical definition, like you are familiar with math, sum and product and everything. And they are evaluated according to the mathematical semantics. And on the left-hand side, there is the code semantic. And by the way, again, I'm not going to check to you, but in fact, when you run it, our tool will find a bug. And our tool will find corner cases, and there are many, many corner cases. So it will find a corner case and tell you that this equivalent does not happen. So just to sort of give you another application of it, here is another example, and it's a beautiful example that came from Jeff Hayes. Jeff Hayes is the CTO of Compound. Compound Finance is a company that builds a money market. So what they do, they have a complex code. You see on the right-hand side, they have a complex code. And this complex solidity code, it determines the new price of the shares. And basically, what they want to know is they want to guarantee to the customer that nobody will be able to steal the shares, or nobody will be able to steal the money. And the way they are doing it, of course, is by using human. So there is a human which is actually has a kind of a 24/7 that it checks this property. But in order for the human to be successful, the code must adhere to certain property. And the question is, what is the mathematical property that the code needs to adhere? So the idea is that what we want to make sure, we want to make sure that the derivative is bounded. We want to make sure that at any point of the time, there won't be a big difference in terms of the money market. So that's basically what will happen. We write this mathematical requirement. We write a mathematical requirement that says that between any 2 points of time, the price cannot change too much. And guess what? You will feed it to the tool, and the tool will identify for you a very interesting case, corner case, in which this is not the case. And you need to fix it. And once you fix it, it will tell you that it's correct. But this corner case is something that will be very, very hard for humans to identify. And this is something that the tool automatically identifies for you. Okay, so it automatically identifies this property. The third property, which is related to what Martin said in the third problem, in the context of the blockchain, the miners can do many, many things. And we want to avoid it. Hopefully, we want to avoid it when we write the contract. And in fact, Satora can help you to do that. So what happened, for example, here are two functions. And one of them, it buys something, and the other one, it sets the price. And what you want to know, for example, you start with a state, one state, then you execute F, and then you execute G, and in the same state, you can start with G, and then you execute F. And what you want to prove that these two they commute. So you want to prove that the purple state is equivalent to the brown state. And this is something that you want to mathematically prove. So once again, you see the CVL. This is the spec that we write in order to check that. So basically, we generalize the product, we generate the price, we generate the initial state, and then we check if there are two executions which start with the initial state and satisfy the property. And once again, the tool will identify a bug for you. It will identify a case that, and I'm not showing you this, but it will identify a case in which this bug occurs. So this is something that you want to write. You write this CVL, and you can check the properties that you want. And the interesting thing is that this CVL, it suffices, you notice in this case, this CVL suffices to check all the reordering. So this is what you are doing. So just to summarize, the CVL, it's allowed you to ensure smart contract properties. At the moment, we are focusing on safety. It's an ongoing effort, so it means that we're probably going to add some more things into that. And we have these three design principles. And we think it's useful for verification, but it can be used for testing. It can be used for other things. And the idea is that you write this CVL, and then we check your properties. So what is the technology here? So as we say, there is a big technological effort. And what we do, we build on the fact that we are actually leveraging academic experience to build the most precise method for verification. And the interesting thing that we really don't want to have verification has been deployed, been developed and been used. But the biggest problem in verification that we avoid in our tool, we want to really give you real errors. So we want to come with zero false positive, basically zero false positive and zero false negative. It means that we're not going to give you any false bug, and also we're not going to miss bugs. And this means that our technology must be very expensive, and in fact it is. But what happened is, what helps us is the modularity. The fact that we can actually verify each of the contracts separately. So basically, this is what happened. We analyze each of the contracts separately, and again, the property of the DAO help us. So this is sort of just the core idea in the technology. So here is the demo of the tool. You see it's a web-based tool. You see that I write here the contract, I write the name. You see now I have to compile, so this is just application of the Solidity compiler. You see you get the EVM. You get the EVM. You see you cut the EVM. And then you run the EVM, you select the CVL file. You see now you select the CVL file. And you submit it. Okay, don't run it now, okay, but you see, you check all of these vulnerabilities. So these are all the vulnerabilities of ERC20 tokens. And you see, we show you for each of the vulnerability. If it cannot happen, we actually can produce a proof that it cannot happen. And when it happens, you see we display the counterexample in terms of the input and in terms of the values that have the error. Okay, so that's it. So how are we going to do and to make it a real thing? So here we need the community. We need you. In the same way that Microsoft Device Driver, we need to understand what are the correctness rules. And this is what we are doing. It's a joint effort, what we are doing with customers and with everybody who's agreed to help. We are actually understanding the correctness requirement. And these are all public domain. These are the CVL. And we are doing it in two ways. We are doing it by formally verifying certain domains, like, for example, stablecoin, money market, ownership, all kinds of properties which are important in this domain. And we are also doing it by developing what we are called continuous verification, in the same way that Microsoft did. So, if, for example, if you are deploying a contract that you did not develop, it's actually very important for you to know what properties it satisfies. And this is what we're going to do for you. So by this, we will establish trust. And so what I presented today is a language for enforcing smart contract security. And we think it's also useful for testing, but we haven't tried. There is also this core technology for verification. This is already available for our customer. Basically, they take a simple jar file where they can run this thing. And also, we are thinking of developing this freemium service, which I demonstrated, and this will be available in March. So thank you very much for your time.
Thank you very much, Mooly. We now have time for a couple questions. I guess we can give it to Matsuo.
Thank you very much for the talk, sir. I would like to ask you two questions. So first is, what is the target of verification? That is relationship between the specification and code or protocol specification itself. And the second question is, how do you verify?
I didn't understand your first question.
So, what is the target of verification?
So the target
the relationship between the specification and code or the protocol specification itself.
So it's the verification of the code. Okay, we want to verify the code.
Okay, and then the other question is, how do you verify the correctness of formalization?
So that's a great question. So we don't verify the correctness. So you are asking, how do we know that the specs that we wrote are correct? So the answer is we don't know that our specs are correct, and that's why specs are very, very difficult. And spec can be, but the interesting about spec, it's a joint effort. So what happened, for example, with our customer, one of the values of this spec is it's a useful thing. So this is the value of that. And also, I should say, we have actually technology that we are showing that give you some kind of sanity check for the spec. For example, if your spec is something that actually is held in a vacuous way, we can actually give you that. Because believe it or not, we also make mistakes.
Do we have any other questions? Hands? All right, thank you very much for presenting to us. Big round of applause, everyone.